Hi everyone, my name is Molly and I am one of your LAs for BSc 2010. So today I'm going to do a walkthrough of our Lac Operon activity that we did through Zoom conference this morning. And the reason behind this is because you guys aren't getting formal instruction, and also I know there was a lot of miscommunication and difficulty using Zoom. So I'm just going to summarize the activity for everyone to make sure you understand what's going on and why we talk about the Lac Operon in Bio 1. So, what is the Lac Operon and why does it exist? Well, all of our cells in our body have the same DNA. Since they all have the same DNA, they have the same genes. But not every gene is necessary in every single cell. For example, if we have genes that code for enzymes that help to break down food in our digestive system, do we want those genes to be turned on in our eyes? Do we want them expressed in our ears or on our feet? No, because they're just simply not necessary. It would be chaotic and that would just be a waste of our energy. So we have gene regulation in order to regulate whether or not genes are on or off. Now, with that being said, we do have constitutive genes that are always expressed, they're always on. But we're specifically talking about gene regulation and operons. So what are operons? Operons are a fancy mechanism for gene regulation that can either be induced or repressed. So today we're going to specifically talk about the Lac Operon. So as you can see on my screen, I inserted your activity into OneNote and also a blank diagram of what the Lac Operon looks like. I want to give you an opportunity to attempt this activity yourself before I just start filling it out. So I'm just going to kind of go through a walkthrough on this blank operon and then allow you to give yourself a chance, and then I will go through all of the answers so you can just pause the video or come back to it later. So, what is the Lac Operon? Well, when we talk about the Lac Operon, we're talking about prokaryotes. This is something specific in prokaryotes, specifically E. coli. So in E. coli, they need a form of energy. So usually to utilize their energy, they choose glucose. Glucose is a monosaccharide, it's a simple sugar, and it's easily accessible. So if E. coli has access to glucose, it's always going to prioritize glucose. That's the easiest way to get energy. What if glucose isn't present though? Well, there's other sugars such as lactose. Lactose is a disaccharide, but it's a lot harder for the cell to utilize disaccharides because there's a bond binding those two monosaccharides together, and so it's going to be harder for the cell to break down and utilize that energy versus just having the glucose as a quick, fast source of energy. So I'm going to show you how the Lac Operon works and why. So, let's start by looking at our diagram, and I'm going to quickly just talk about the role of each thing on this diagram before I just start drawing pictures. So, as you see, we have an operator. This operator is where our repressor is going to bind, which I will explain in a second. Then we have a promoter. This promoter is where RNA polymerase binds. So you can remember P polymerase, RNA polymerase. And then we have an activator. We're going to talk about the activator when we talk about CAP and cyclic AMP. So we'll come back to that later. Then you can see right here, we have this LAC-I gene. What this LAC-I gene does is code for the repressor that's going to attach to the operator. And over here on this part of the operon, you will see three genes, LAC-Z, LAC-Y, and LAC-A. Specifically, LAC-Z helps to hydrolyze lactose, LAC-Y helps to allow lactose into the cell, and LAC-A helps to remove toxic byproducts. So overall, more important than the specific jobs of each enzyme, we mainly need to know that these are the enzymes that need to be activated in order to successfully break down lactose and utilize it as a form of energy in our cell. Now that I've confused you with all of this terminology and all of these words, let's take a second, put it all into play so that the Lac Operon can make sense. So in order to do that, let's just start with our first scenario. In our first scenario, we are going to have no lactose present in our cell. So, when we talk about the Lac Operon, what is its purpose? The Lac Operon's purpose is for RNA polymerase to transcribe these three enzymes that are going to help break down lactose. But In this scenario, we have no lactose. So use your common sense, sit back and think. If we have no lactose in our cell, what is going to happen with our Lac Operon? Well, it's simply going to be turned off. Is there any point in the cell wasting energy to transcribe Lac Z, Lac Y, and Lac A if there's no need to break down lactose? No, that's just a waste of energy, it's unnecessary, and these enzymes would just be free floating in the cell and have no purpose. So, no lactose, we have this thing that's always bound to the operator by default, and this is our repressor. So let's pretend that this little pink circle I'm drawing, bound to the operator, is the repressor. So I want you to think of the repressor as a barrier in the way. He can be an angry man sitting on the operator. He can be a barrier on a train track. He can be whatever you want him to be. But just know that that repressor is bound to the operator. It is not going to lift off until you have something good to offer him. What the repressor wants is allolactose. So now in our next scenario, we're going to say, what would happen if lactose is present in the cell? So if lactose is present in the cell, it's also going to have an isomer present in the cell. So pretend that this little circle is lactose. Well, if lactose is in the cell, it's also going to have an isomer called allolactose in the cell. So we'll make allolactose like a little heart or something. So we have allolactose in the cell. What does the repressor like? He likes allolactose. So what allolactose is going to do is it's going to bind to the repressor right here, and that angry barrier, that angry man, that train track barrier, whatever you want to think of him now, it's going to change its shape and lift it up off of the operator. So when lactose is present, allolactose is present, and allolactose binds to the repressor and lifts him up off of the operon, and he's a happy little dude because he got what he wanted. But now this is an opportunity for RNA polymerase to bind to the promoter and transcribe Lac Z, Lac Y, and Lac A. So the repressor is off of the operator, allolactose is bound to the repressor, which changed its shape, allowed it to lift, and now RNA polymerase is able to bind to the promoter, move down these train tracks, and transcribe Lac Z, Lac Y, and Lac A, which are all going to break down lactose. The Lac Operon isn't as simple as that. We also have to take into account glucose and what happens when glucose is also present in our cell. For our last two scenarios, we did not consider glucose, but now we need to consider glucose. Why? Glucose is the preferred source of energy for prokaryotes because it's a monosaccharide and it's more easily accessible than lactose. So now we have to consider two new things. We have to consider this yellow circle right here, which represents CAP, or the catabolite activator protein, and we also have to consider this little red circle right here. All of these little red circles, what are those? Those are CAMP, or cyclic AMP. Well, there's a relationship between glucose and these different things. So CAP is an activator protein, and what that does is it binds to the activator when it's in the presence of CAMP. And then when it binds to the activator, it's going to allow RNA polymerase to bind to the promoter more quickly and then transcribe these genes at a much faster rate. So, in our specific scenario here, we know that there is no glucose. So if we follow our little rules right here, we know that when there is no glucose or glucose levels are low, CAMP levels are going to be high. Why? Well, when glucose levels are low, we want transcription to happen at a very fast rate so that we have the enzymes that we need to break down lactose and use it as a usable form of energy. So, we know that there's no glucose. Since there's no glucose, CAMP is going to bind to CAP. And then when CAMP binds to CAP, CAP is going to bind to the activator, therefore allowing RNA polymerase to more quickly bind to the promoter. Well, in our example, we also know that lactose is present. What happens when lactose is present? Well, when lactose is present, which is this little red circle right here, we also know that its isomer allolactose is present. As we learned earlier, what happens when allolactose is present? Well, allolactose is going to bind to the repressor because that's all he wants. He's a stubborn little guy that just wants some allolactose. And then when he gets his allolactose, he's going to lift up off of the operator. therefore allowing RNA polymerase to move along this strand of DNA and transcribe these 3 genes more quickly. So something I forgot to mention earlier is LAC-I, the specific gene you see right here. Its purpose is to form this repressor. So LAC-I's purpose is to form the LAC-I repressor, which is this little guy right here. So I'm going to do another scenario, and then we will do one more quick review of the vocab. So for our very last scenario, we're going to talk about what happens in a cell when glucose is present and lactose is present. Well, what do we know? When glucose is present, CAMP levels are going to be low. So we have our CAP here, but we don't have any CAMP. These little CAMP cyclic AMPs, they don't exist right now because glucose levels are high. Therefore, there's no need to speed up transcription because the cell would prefer to utilize this glucose as its first source of energy. So, So, CAP is not bound to the activator, so the activator protein is not going to be bound to the promoter. But we also know that lactose is present. And what happens when lactose is present? Well, when lactose is present, allolactose is also present. So this repressor that is by default bound to the operator has allolactose bind to it, therefore lifting it up off of the operator and allowing RNA polymerase to bind to the promoter, move along the track, and transcribe LAC-Z, LAC-Y, and LAC-A.